Hi everyone. I would like to start with the talk from objects to functions. Today I would like to take you on a journey, on my journey from object-oriented programming to functional programming and back. I will start. I won't. Now I will. With identifying 4 quadrants of programming. When we are writing code, we do write code of 4 types. There might be some other, but those are the basic ones. Even if we do it consciously or not, we do it. Remember those quadrants because I will get back to them throughout the presentation. Let's say I am an object-oriented programmer. Say it loud and proud without anyone laughing. I already heard someone laughing here. Is it even possible? I do some talks. I go talk on meetups, and whenever I say I'm an object-oriented programmer, I'm being laughed at. Why is that? I think something went wrong with our way of writing code. What went wrong, or how is it possible? I can't get. Even big names of our industry, like Mr. Dijkstra, is saying object-oriented programs are offered as an alternative to correct ones. Or Mr. Alan Kay, the founder of the term object-oriented programming, he's saying it's unfortunate that much of what is called object-oriented programming today is simply old-style programming with fancier constructs. So there must be something wrong. Hello again. My name is Dominik Moštěk. I consider myself a software craftsman. It's because I'm always unhappy with the code I write, with the code everyone around me writes. And currently, I'm part of an Atacama company, and we are building the future of data management. Please ask questions throughout the presentation using the Slido app, inputting the GeeCON 2022 code, and selecting the room 6. About Atacama, about my company, we are building a data product which helps our customers to build their business on their data, to see what data they have and how they can utilize them, from data catalog through the data quality to showing the data using data stories and other tools. You might heard about us recently. We raised a pretty decent amount of money in our first series of investment. So if you wish to be part of our journey, ask me or go to our website. But now, back to the point of why we are here. When I finished college, I hated Java. I hated everything about it. I was a C guy, I was a C programmer. And it happened that I joined a company that was using Java. I took it as a challenge. I will learn OOP from the grounds, and I will be the best at OOP. So what do you do when you want to master something, when you want to be the best in something? You Google it. So I Googled what OOP is and what should I learn. If you take a look at those pictures, there are some repeating terms. So it must be an abstraction, polymorphism, encapsulation, inheritance, and classes. So I went, learned all those concepts, how to do them in Java. But after some time, I realized I'm writing different code than before, that's for sure. But I haven't seen any benefit to it. It was It had the same amount of bugs. It behaved the same way. It was just written differently. So why? Why we are doing this? What's the point? To get to the point, I think we need to take few steps back into the history and explore what was at the beginning of object-oriented programming. So back to the foundations. Why we even are talking about programming paradigms, about different technologies and so on. There must be a reason to have many paradigms. The reason is that from this book, the reason why we even try to do something better is that the goal of software design is to maximize its value while minimizing the cost of the software. That's a paraphrased content of this book, which is highly recommended. What's the value? That's the features we are adding to the software. But what's the cost? It turns out that the cost of the software is cost of changing it as it evolves. When we are talking about changes, the book also identifies that the changes are tied to coupling. So higher the coupling, the more it costs to change anything. So meet Mr. Alan Kay, the founder of the term object-oriented programming. He was also aware of this problem, and he tried to solve it somehow. And to understand how he tried to solve it, we must know an interesting fact about Mr. Kay. He's originally not a computer scientist at all. He majored in biology, to be precise, in cell metabolism, and he was looking at how small organisms and small living things work the same way the big organisms do. So he said there must be some simple mechanism that controls the complex processes in the big organisms as well as in the small ones. He identified that this simple mechanism is a way how cell communicates and maintain their integrity. This is called an endocrinosis, and it's a way how cells work in all living things. The cell communicates with the rest of the organism by releasing hormones. Those hormones are recognized by other cells. All that is happening without each individual cell knowing anything about the rest of the system, about the rest of the organism. So they maintain their integrity. So how this relates to computer science, to programming? Mr. Kay translated this into a sentence. OOP to me means only messaging, local retention and protection and hiding of state process, and extreme late binding of all things. I will shorten it a little bit. So those are three key principles of object-oriented programming. Messaging represents the act of releasing the hormone and traveling to its destination. Local retention is a short word for the integrity of the cell. So each object should return their state, hide how they are doing the things. And extreme late binding is the property that those messages, those hormones, are actually fire and forget. You just release them and don't care about anything else. You don't know about the recipients, if there's one or many. Just don't know at all. So we then identified the key principles, and now let's compare them to the results I found on the Google. Without any doubt, I will say that inheritance and classes does not reflect anything about the objects about properties of the object-oriented programming. You don't need classes or inheritance to achieve any principle of object-oriented programming at all. And those three, abstraction, polymorphism, and encapsulation, is just a way, one of the possible ways how to implement it. It's not a single one. There's no single one. There are many. Those are being one of them, and they fulfill the principles only to some extent. When you look at the principles on the left, the ones from the Google, I can say that they are very focused on the language, on the programming language itself, not about the system we are writing, but about the language. So maybe this is where we took the wrong turn. Maybe it's not about the language at all. Maybe object orientation is about designing the system without any language at all, or independent of a language. Let's take a look at some examples. I will start with an example I consider the biggest object-oriented system ever invented: the internet. The internet is the biggest thing our humanity probably has done, because it's scaled so much and it keeps growing. And if you look at it, it actually fulfills the principles to a greater extent than our encapsulation, polymorphism, and so on. The internet is built on a simple networking, but repeated many times at a scale. And it works because it's based on object-oriented principles. It is based on messaging. All those messages are very late-bound. And all the nodes on the internet actually hide their state. Like if your server is offering their inner state to outer world, your security is not very good. So what it allowed us is actually to scale at, I'm not saying at no cost, but at low cost, which is definitely not scaling the same way the number of users on the internet is scaling. And we are not talking about the features internet offers. This is just number of the users. But get back to the code. So how is messaging usually implemented? This is a code I guess most of you have written in your past. And it might be a perfect object-oriented code, but at the same time, it doesn't have to be. The messaging here is done through the simple polymorphism. So that's the usual way. So the author of this code made a decision that this code, the notification at the end of the user registration process, is subject for a change. It will change in the future, the way how the notification is sent, the means of the transportation, or anything about the notifications. Another example of the same registration process. But in this case, the author made a decision that the whole process is subject to a change. Anything about registration can change, not only notifications at the end. Each step can change in different ways. So he made some cleverness around his messaging. Now, the invocation of the on method on the event is not the messaging. The thing that we are using some event bus is the messaging, that we are putting the messages into some queue or anything, and the queue invokes the targets. So that's the messaging, not the polymorphism. The polymorphism is just an implementation detail of some language we are using here. The important message here is, key takeaway, is that there is not a single silver bullet answer to what object orientation is, or messaging is, and how to implement it. It's about making a conscious decision about your system, about how it will change, how costly it will be to change it, and what are the changes we are preparing for. Some of you might know domain-driven design and the technique called event storming. it identifies what events we do have in the system, at least on the high level. It is actually a great technique to identify those events, those messages happening in your system. What I am trying to say here is that sometimes I hear that domain-driven design is an alternative to object orientation or anything like that. It's not. It clicks together like puzzles. So domain-driven techniques actually allow us to create great object-oriented systems. But to the next principle, local retention. This is the simplest example I could think of. The notification service, in this case, is leaking some abstraction that it uses a MongoDB inside. This is, of course, not good, but obvious. This is obvious that there is some leaky abstraction here. But what about this? This is a code I encounter a lot. There is, you already know law of Demeter, right? I like when it is phrased as law of least knowledge. So we shouldn't assume anything about our objects. In this case, we are assuming that we will get a return value, that it is a synchronous operation. Maybe it was a conscious decision, but maybe it wasn't. And the author of this code was just assuming that we are on the same JVM, we can do whatever the language allows us, so I will return a value. But what happens when we move this object into some distributed environment, into cloud or into microservices, you name it? This would be maybe possible, but maybe not. If I move to the message broker, this might not be possible at all, or very costly. The second line, it's basically the same thing. It's leaking that there are data prepared after the object receives the message. Will this always be true? If I move to asynchronous world, won't be true anymore. And also, I'm getting the data. I am violating the principle, the local retention, because I am pulling something out from the internals of the object. This might not seem that bad, but again, what if I move to microservices? This will happen to be a HTTP call. And you've got the distributed monolith. This is the birthplace of distributed monolith. And last principle, extreme late binding. A simple polymorphism here. It is a light binding in a way, but definitely not extreme. As I said, it's a scale. So if we anticipate small rate of changes, which are not that costly, we can stick with simple polymorphism. But if we anticipate more changes, we might tweak it a little bit. This is the smallest possible iteration I could think of. We are just saying, okay, there will be more targets of the message. So I'm still using the polymorphism, but I made a little step towards more extreme late binding. Another step might be to move to some event bus, to message broker. Message broker here is basically only an implementation detail of the event queue. So it's a scale. Key takeaway of this part is you should use object-oriented programming to prepare your system for future changes at appropriate scale. You don't do event buses for changes that probably won't happen, and if they happen, it costs one man day to make them. So use appropriate scale. And to the core of this presentation, from objects to functions, I have used object orientation to create the system, to design it, to identify the messages, the patterns of message transfers, and everything. But now I need to actually implement the functionality, the behavior of the system. So what I'm left with, if I leave aside the object orientation, because I used it to design the system, and I will leave aside some edge paradigms as logical programming and so on, I am left with imperative programming, which is the mainstream today, I would say, and functional programming. And of course, you know which paradigm I will talk about the rest of the presentation. So if you forget that the class represents an object, because object can be anything, class is just a way how to organize your code. And I can look at a class as a set of partially applied functions. What do I mean by partially applying a function? This is an example from Python. I've got a function which takes 2 arguments, and I'm partially applying one of those arguments with an hard-coded value. So I get a partially applied function Google Mail, which has only 1 argument as an input instead of 2. If I transfer this into a Java, constructor is just a way how to partially apply all the functions inside that class. So your method is a just partially applied function. The partial application is on your fields which you input into your class through the constructor. This is a subtle difference, but from now on, think about classes as partially applied functions. When I'm moving into the functional code, let's repeat what functional programming principles are. It stands on pure functions. It means that output of a function is based only on its inputs, nothing else. That, wrong order. I can compose the functions to create more complex functions. And if I replace any part of that functional composition with return value of that function, I'm being referentially transparent. I replace it with a value it returns. It works the same way. So 3 primary principles of functional programming are pure functions, functional composition, and referential transparency. There are others, but they are more or less derived from the primary ones, so I won't use them that much. I will focus on the primary ones, on the 3 first ones. So again, the example, a simple portfolio service. It computes how much you lost on your Bitcoins already. So I've got a wallet repository, which gives me how many Bitcoins you have in your wallet, and just do some very simple computation with the current value of those Bitcoins. Remember those quadrants? We moved from the design into a function one, but here I'm mixing actually the functionality, the algorithm of computing the value, with something I call plumbing. This is connecting things together. So let's segregate those apart. So I will segregate the computation, my algorithm, into a separate class, and it becomes a function, simply. It's pure, it depends only on its inputs. It's referentially transparent. It's not seen on this very simple example, but I can replace any input. I'm omitting the constructor here, of course, with some other functions, as we will see in next slides. So it's pure, it's referentially transparent, and it's composable. Now you can see that it's not a portfolio anymore. It's just a simple product. So I created a very generic function. And I will, when you try to do this, when you extract the functionality from your plumbing code, you will see patterns. You will recognize very common functionality among your functions. Let's plug it back into the plumbing. I can hear your voices. Dominik, you're poor soul. You have the same functionality with more code. This is insane, I'm not doing it. But bear with me, it has its benefits. One of them is the separation from the plumbing. So I'm actually sticking to the CRP, single responsibility principle. The second one is that the only way how to reuse the algorithm from the first slide is actually to copy-paste it. Now, I can reuse it because I have the function as a separate object or separate entity in my system. So I can reuse it, I can test it, but we will see the benefits on the next slides. One of them being I can compose it with another functions. In this case, I added a caching. It's not a side effect free function, as you would expect, but we have to have a side effect somewhere in our system. So I'm caching the value from the exchange. How is that possible? I had an integer there. Unfortunately, Java is not very prepared to compose functions for primitive values. So I can't have, it's not an interface, I cannot implement integer, so my function doesn't represent an integer. So I have to do some engineering around it. You can have something like a variation of supplier, or you can use supplier itself. This applies to primitives in Java, in types you don't own. For your own types, you can accommodate the code so you can reuse it. So I am using the interface segregation principle from Solid, right? I'm having very small interfaces so I can compose them. I brought an example of functional composition from someone called Yegor Bugaenko. In his blog, he has many examples. This is how you compose functions. The only difference between what I'm telling you and what Yegor is saying is he still calls this an object orientation. Might be, but I think it has all the properties of functional code, so I call it a functional programming and functional composition. And the last property is referential transparency. So I can replace the cached value or call to the exchange, call to the repository with the values it will return, and it has the same output. This allows me to test my code very thoroughly without any mocking, without any test database or anything. I can have very simple unit tests for my functions. I will also mention side effects because we have to have side effects in our code. Such stateless software would be probably useless. It doesn't mean that we don't have side effects in our functions. We just have functions that have side effects and those that don't, and we segregate those strictly. So if I want to put a side effect into my functional composition, I do it the same way as I would compose any other functions. I just plug it in my plumbing code. So I actually applied some best practices known from object-oriented programming world, like Solid. Don't repeat yourself by reusing the code. My functions are immutable, everything is composable. So I applied best practices from OOP world, and I ended up with functional code. Okay, but why? Why should I do the extra engineering, the extra coding? I should get some benefits. There are many. I identified three which are most important for me is testing. So as I said, the referential transparency allows me to test my functions in complete isolation. So now you will have your testing pyramid on a solid ground. You don't have to bring up your Spring context, so you have a repository to test that the algorithm computing the value of a portfolio is correct. You just test the function which computes it, and then plug it into the system. So you will have a lot of unit tests because it's so easy to write them. So testing pyramid on the solid grounds. The reuse, if your functions depend on very small interfaces, it's very easy to reuse them. In this case, I have a report value function which reports the value being read to some system, logging maybe. I can reuse this functionality very easily. It's small, it depends on small interfaces, so it's easy to adapt it to any code you have. So it's reuse. And my favorite one, it reduces cognitive load by being declarative. This is something I found on the internet a few years ago. On the left, you can see an imperative code. Each color represents some concern we are solving in the code, reading from a file, collecting errors, filtering, so on. In the imperative code, all these things are scattered around your method, your code. On the right, on the internet, this was called a functional approach. I wouldn't call it that way, but it's a declarative for sure. Now, I've got all the concerns line by line, nicely arranged, so it reduces the cognitive load needed to read the code. And I can choose the level of detail I want to go into. If I'm interested in how these things are filtered, I go into the limit function. If I want to know about how the file is read, I will go into the first read part of the code. So I don't have to read the whole code to get single information. If I rewrite it to the approach I showed you before, it might be something like this. I like this even more than the first example because this for me reads as, let's say, an English sentence. Like, give me 40 error lines from a file. So I've got some filtering function, some limiting, filtering, and reading. The reading being the least important from all of them because the source of the log lines might change to database, to some external system or anything, but the rest will stay the same. So I've got code that can be very well tested, which is reusable, which is easy to understand because of its declarativeness. And what I'm getting at the end is a maintainable code, which again lowers the cost of the software as it grows. The idea of why we even care about anything in computing. So what is the future? I was part of endless debates about should I write object-oriented code or functional code. I don't think this is the debate. The debate should be how we can connect objects with functions to achieve best software. So I think we should use object-oriented design for our systems to prepare it for future changes, implement it functionally to have all these benefits I was talking about, use domain-driven design to help us with identifying the events or other aspects of our system. Also use it for identifying your types, your ubiquitous language, as domain-driven design calls it. And of course, all your code should be clean, right? So clean code is about all those quadrants I was talking about at the beginning. when I was talking about those quadrants, we have one language we are writing our systems in. But that doesn't mean that all code is equal. We should focus on different things in different quadrants of writing the software. So when I'm in the design phase, I care about the messages. What messages will be there? How to design those messages and this eventing system that it allows to scale the system and to how to support its changes throughout the time. When I'm in the functional quadrant, I care about how testable those functions are. How can I reuse them as much as possible? How to compose them to achieve more and more complex functions. When I'm in the plumbing code, in the services, I care about proper layering, about proper structuring of the code. So it is easily navigable. I'm not reading data from controller directly. That's where you control the layers. You also adapt your error handling in your plumbing code. When I'm in the types quadrant, I care about designing my classes so they represent the ubiquitous language, my domain language, and I can use the inheritance for that. And in different quadrants, I have different requirements for my code. So in the plumbing code, me personally, I don't do much unit testing. It doesn't make sense for me. I do some integration testing, but not unit testing. I've got most of my unit tests in the functional world. In the design quadrant, it's mainly about interaction with your colleagues, about discussions, analytics. And in the types, it's about how to understand your code better to make it more readable. So the key takeaway of this talk is that it's okay to have one language, use both paradigms to create scalable and maintainable systems. So adding value at low cost. Thank you very much for your attention. Thanks organizers for awesome event. And I hope I have collected some cool questions. Okay? I will try. I will try, but I don't know how. We can read this question, or we can read them out. Okay, I will use my phone because I don't know. The first one is always the most upvoted one. Okay. One thing to mention, I've got some Atacama merch here, so 3 top most voted questions will get some Bluetooth speakers. First question is, how difficult is to find developers willing to code in a functional style in Java? Oh boy, very hard. I found it easiest to start this with junior programmers because they are not, how to say it, indoctrinized. I'm not finding the right English word, by the whole OOP movement, and we can actually influence them into the correct way, right? How would you deal with exceptions? Not sure what is meant by that, but I guess general error handling. Your error handling, again, it depends, but it might be just a message sent out of your object. If you mean like throwing exception out of the object, you can design your system that this is actually the output message from your object. It's fine, as I said, it's a scale. If this is okay for you, that you are coupled with the exception being thrown synchronously from your object, that's fine. But if you anticipate a lot of changes or moving this object from single JVM to a microservice, I don't think that exceptions are a way to go. Next question is, in your filtering example, how would you rewrite it with your DB? You probably wouldn't load the entire table into memory, right? Yes, I wouldn't, but the code would still be the same. I will treat the filtering from the database as an optimization. So I would still have in my code the limit, the filter, and the reading itself would be a function that gives me pre-filtered values from the database. Why I'm doing this is because I can capture the requirements for the software in the code. It suits me the best. I can unit test it, and if the source changes, I've got my unit tests covering the requirements. Are there any open source Java projects or libraries built on those principles? Some good examples where we can see them applied properly and nicely. The Yegor Bugayenko, if I'm pronouncing the name correctly, has a library called Cactus, I think. He has plenty of functions ready to use. So I would recommend this one. There are unfortunately not much open source code that you can get inspiration for the object orientation way, because that's very tightly coupled with the business and with the context of each company, of each project. So you won't find, I don't want to say any, but it's very hard to find. Testing individual functions seems easy, but how do you test that your program actually composes those functions properly? Again, I'm using different approaches. Sometimes I'm using something like, I would call it a factory method. So I just compose those functions, leaving the side effects as an input to this factory method. And in my unit test, I test this composition through this factory method, and as an input, I am, instead of the real dependencies, the database and so on, I'm putting some array list or something. There are different approaches. You can create a class that represents actually the composition. So only thing in that class will be that composition, that's all. It won't have any other code in. I think I recently started coding in Kotlin. I think Kotlin makes this even easier. You can do some better ways in Kotlin, but when I stick to Java, I use those two approaches. So, what do you think the disadvantage of this approach is? Any problems you have encountered in practice? The biggest problem is actually the question number one, finding people who are willing to do this, let's say, mind shift and code it like this with you. There are, of course, disadvantages, like in the plumbing part of the code, sometimes this won't get messy a little bit, because as the plumbing and getting things together becomes more complex, this is a real challenge. Setting transactional boundaries, for example, it's not hard, but it takes a while. So the plumbing code becomes sometimes hard to read, and the thing with your colleagues, that's the biggest challenges. Your examples create orders of magnitude more objects than what is needed in traditional style. Java is not ready for these performance matters. Are we too early? In the book, I showed the structured design. That's a book from 1972, I guess. So it's 50 years already. And on, I don't know, in the first part, they say, you should do proper design, and we are ready for this. In 70s, they said that you shouldn't care about creating too much objects, too much functions, too much anything. Just create perfect design and solve this in the future. They saw it as a premature optimization. And I see it the same way. I actually once rewrote a big chunk of a system to this functional style, and it was actually a great success. It was a very time-sensitive part of the application, and everyone was like, okay, we are now creating thousands of unnecessary objects here. It will be slow as hell. The result was that it generated some contracts to the future to be traded. The original function or object processed this, I think, for 5 minutes, and we get to like 10 seconds. Even when we were creating so much objects, the fact is that the modern JVM is so smart that it will create unthinkable optimizations to your code. And when your code is simple, it can do better optimizations. So if you create a lot of simple parts, it will optimize the hell out of your code. So it will be very fast. How does debugging look like for a large enterprise applications writing functionally? I think it's actually the same. What you have seen, the composition, that's actually a call stack of your app materialized in a code, right? So I would say it's the same. It's just written very explicitly. I haven't encountered any difficulties debugging this code. How do you deal with checked exceptions in functional code? I don't think I'm able to answer it because I don't use check exceptions. So maybe don't use them. I don't know. Do you think using Java in functional way is counterproductive, since Scala is much better prepared for functional programming? I hoped this question would be the first one, actually. Yes, there are languages much more prepared for functional programming, Clojure, Haskell, Lisp, everything like that, or Scala, or even Kotlin. The thing is, I just chose, sorry, this is the hill I chose to die on. What I have to say about it is the mainstream coding. Java is the most used language on the backends, I think. So I just chose that I will like make our code better without moving away. If all of us we want to write good code, and I think most of us want, but that's why you are here. If we all move to Scala, we will be on the Java side. All those ones writing the ugly code, right? And we can't let this happen. I think, yeah, it's 8 seconds to the end. So thank you for all the questions. They were wonderful. And please, if you remember who was the 3 top voted ones, please, please meet me here. I got some gifts for you. Thank you.